Hi, let's do some calculus. Woo woo! That was 2 woots. Let's go. We're on daily lessons 203 to 205 in the 200s. This is a good day. So this first question says, how have we found average velocity? You may be thinking, I don't know. So let's think about this. Average velocity. What would be a good unit for average velocity? Or just velocity? Meters per second is a pretty common one. You could do miles per hour. You could do any other position over some time. And so if I'm thinking about this and I'm thinking position, I'm going to say P of B minus P of A. So the change in position over some interval of time. And think about position when we measured in, let's say, meters or miles or inches or something like that, some unit of measure. And then B minus A is some unit of time. So meters per second, oh yeah, that makes sense for average velocity. So if I would say, so to find, sometimes you'll see it like that, VAV, the velocity average, on some interval A to B, so this is some closed interval, find the slope of the secant, or the slope of the secant line, of, and I can say of position function, so of P of T. Do I want to say of B, from A to B? From, or on interval A to B. Okay, so this is what we did. P of B minus P of A over B minus A. This is the average velocity. This is what we found before if we were talking about the velocity over some interval of time. Average acceleration. How do you think we did that then? Think about what the units would have to be. Okay, common units for acceleration would be like meters per second or meters per second squared. How would I make the numerator meters per second? Yeah, by putting in velocity, B minus A. So then the numerator would be, let's say, meters per second over seconds. That would be meters per second per second. Same idea to find AF, and this, the same thing on some interval from A to B. Find slope of the secant of V of T. So same thing as up above, is just to find the A average, we're finding the slope of the secant line of V of T. Okay, so we've got this, and you've already done this before. It's just been a while, so I'm just trying to bring this up into your memory, or recall it from your memory and bring it into your current thinking. And now we're going to think about if P of T, V of T, and A of T represent position, velocity, and acceleration. So position, velocity, acceleration. And remember that position, if you take the derivative, you get velocity. If you take the derivative velocity, you get acceleration. For any time t, write an equivalent expression of each of the following integrals, okay, based on the fundamental theorem of calculus. We can do that. Fundamental theorem of calculus. Hopefully that's coming to your mind now. I'm going to do something really crazy. This is going to look like advanced technology. You're going to look at your paper and say, whoa, how did hers disappear? But it's just going to be my finger. What? I want to know just what's that. I can do the area under the curve of A of T, but I don't have a curve of A of T. So what I need to do is think about the fundamental theorem of calculus. What is the antiderivative of acceleration? Or an antiderivative? Velocity. So according to the fundamental theorem of calculus, the integral from A to B of A of T dt is V of B minus V of A. See this 1 over B minus A? If I multiply this integral times 1 over B minus A, that's the same thing as dividing by B minus A. What? What is that? Oh my goodness, this is so exciting. This is average acceleration. What? That's what we just found up here. Okay, what about this one? I'm gonna do the magic again. Be prepared. I did it. Okay, so do this one. What does the integral of from a to b of v of t actually equal, if I do the fundamental theorem of calculus, that would be P of B minus P of A over B minus A. And I get average velocity. Ta-da! Do you notice how in this first one I integrated A of t and then I divided by b minus a and I got back to average acceleration? So there's A of t inside this integral and then now I'm suddenly back in that same place. So integrated, this is like taking the slope again when you divide by b minus a. Same thing here, I'm integrating, dividing by b minus a, I'm back to velocity. We can actually do this with any function. If I start with some function, let's say f of x. Oops, sorry, my face is in the way. There we go. F of x dx. If I want the average function value for f of x, whatever f of x is, I can integrate and then divide by b minus a or multiply by 1 over b minus a. Usually say it like this. So this is really exciting because I can have the average value of any function, not just velocity or acceleration. Okay, let's do another one. So in this one, find the average value of the function. So now I've got this guy on this interval from 1 to 3. And this one says it's a calculator problem, which I should look around for my calculator. Oh, found it. Sometimes my son plays with it because it's a super cool thing to want to play with. Okay, so on here, so I'm going to say this. I'm going to integrate from 1 to 3. And here's where you can actually just write f of x dx if you want, or you can write it out. X cubed sine squared x. Don't forget the dx. But this would give me the antiderivative, like the antiderivative capital F of 3 minus F of 1. I don't want that. What I want is the average value. So as soon as you're seeing this, think 1 over b minus a. Okay, and then how you do this, get your calculator. I'm going to do this together. I'm actually going to move it up so you can see a little bit more. I'll move it over here. Okay, if I push math, and then I'm going to go down to 9, or if you go the whole way till you get to the integral one. Oops. Don't do that. Math 9, there we go. And I'm going to go from 1 to 3. X cubed. And then be careful how you put in this next part. This is the same thing as sine of x. Do you notice how I have this whole sine of x squared? Because this means this whole function, sine of x, that whole thing is squared. Make sure you don't just put sine of x squared or your answer is going to be wrong here. Then I put dx. Oops. And I look and I see I did something wrong and oh, it's right there. That's where I did something wrong. There we go. And I get an answer of 8.319. Hold on, I did something different here. Old me has a different answer. Okay, so we're going to put this in our calculator. We're going to say math, and I'm going to go down to number 9, and I'm going to go on this interval from 1 to 3. And then I have this quantity, x cubed square root, and then you have to be careful when you put this in. This is going to be the sine of x squared. Oopsies. Okay, so this one's kind of weird because I'm saying I'm integrating, and really this is kind of weird to write anyway because this is the sine squared and I'm taking the square root, but I'm just going with it and writing exactly what they have. I have x cubed. And there's sometimes, I actually debated this where I was like, is this a cubed root or not? You can always ask me about this, but I have an x cubed and then the square root of sine squared of x. Make sure that you write it as sine of x squared, and I get this, and I see, okay, I've got 11.69363, but don't forget about multiplying that by 1/2. 11.69635,406. I'm not truncating or rounding until the very end of this, but I'm doing times 1/2. Now I can do 3 places after the decimal. Let's do another one. Okay, find the average value of the function. So again, average value, and this one says non-calculator, so let's get this bad boy out of there. Average value of this function. So anytime you're thinking average value, think, okay, I know I need to integrate. I'm going from 2 to 6. This would be 1/6 minus 2. You always want the average value of the function you're trying to, or that you're given in this case, the average value of this function. 2 minus 4x. Okay, now we have to do this by hand. So there are a couple ways that you can solve an integral. The first way is find the area in the curve of 2 minus 4x. I don't really want to draw that graph. It's not given to me. I could, because it's not really hard. So if I had graph paper, I could do this. Or I could do, what's the second way to solve an integral? Fundamental theorem of calculus. So here I'm going to say this is 1/4. This part I'm going to integrate. So the antiderivative of 2 is 2x. The antiderivative of 4x squared, add 1 to the exponent, divide by a new exponent. And then just to be sure that you did this correctly, I would actually take the derivative. The derivative of 2x is 2, and then I get negative 4x, we're good. I'm going to evaluate from 2 to 6. Remember, f of b minus f of a, that's, you have to substitute in 6, substitute in 2. So if I substitute in 6, I would get 2 times 6 minus 2 times 6 squared minus, this is like the f of b minus f of a, or in this case, f of 6 minus f of 2. So this is what I'm doing right now, by the way. And now I would have to put in 2, so 2 times 2 minus 2, 2 squared. And here's where I just try not to mess anything up. There's a saying in my nerd group that calculus is easy, it's the algebra that's hard. This is where we've got to make sure we don't make up any mistakes. Okay, so I've got 12 minus 6 squared is 36, times 2 would be, what is 36 times 2? It's early. 72, there it is. This would be 4 minus 2 squared is 4, times 2 is 8. $12 minus 72. Well, 72 minus 12 will be 60, so this would be negative 60. Minus, this would be negative 4. Negative 60 plus 4. 1/4 times negative 56 would be the same thing as negative 56 divided by 4. Which, checking with old me, that's what I got before. Woo! Did it! Yeah, that's where we cheer for a little bit. Okay, so look through this page. Is there anything that you're not quite sure of? Anything that I can help you with? Ask. This is really important to find the average value. So average value of any function, we do this. That is different than the average rate of change. If I wanted to ask you for the average rate of change of f of x, so average rate of change of f of x, that would be the f of b minus f of a over b minus a. There we go. So just so you know, this is different. Just important to know. Okay, let's do another page. Oh, this one's a fun one because we actually get into it. Okay. This actually combines a whole bunch of stuff you know, and I would say this is more practice than it is a new process, but I'm still excited for it. So a ski resort uses a snow machine to control the snow level on a ski slope. Over a 24-hour period, the volume of snow added to the slope per hour. So I'm starting with a rate. So the volume of snow added. So this is the rate that is being added, is S of t. The rate at which snow melts. So this is the rate at which snow is being taken away is by this function. So we're starting with two rates. And now we've got both S of t and M of t have units of cubic yards per hour. So this is another indication that we have a rate here. And t is measured in hours from 0 to 24. At time t equals 0, the slope holds 50 cubic yards of snow. So we've also got this initial value. We've got so much stuff just already. Okay, compute the total volume of snow added to the mountain over this first 6-hour period. Okay, all I'm doing is figuring out how much snow is added, not how much snow is on the mountain, just how much is added. So let's think about this. I'm given this rate, and I want to know how much snow is added. I have to integrate. And I'm going to integrate from 0 to 6 of S of t dt. Okay, so this is definitely a calculator problem. If I find my calculator, because I kind of hit it a second ago. But because if this is the rate, this would be cubic yards per hour. If I integrate this, this is just going cubic yards at 6 minus the cubic yards at 0. It's how much snow is added. So here I'm going to go, math, and then 9, and from, ooh, that's not what I want to do. If you try to graph an integral, it, your calculator will just keep spinning. 0 to 6, silly. Okay, S of t was 24 minus t, but we're going to do x. Be careful with this. This says sine squared, so I need to put parentheses around this entire thing. I'm going to do sine of x over 14. Close that parenthesis. Close the next parenthesis. I'm going to square it. And then, hold on, make sure I've got this all right. And then I should have one more parenthesis right there. Yeah, I'm good. See what I did wrong. Oh, forgot a dx. There we go, and we get 142.413. And then I can stop 3 places after the decimal. This is the final answer. And it says compute the total volume of snow added. Make sure that you put units on this. I'm back to cubic yards of snow. Okay. Now the next one, it says find the value of this and this. So I have this integral from 0 to 6 and then 1, 6, 0 to 6. Using correct units, explain each. So let's just do the first part and we say math 9, 0 to 6. And then I'm going to put in m of t, which in this case is 10 plus 8 cosine of x over 3. And one more parenthesis there. There we go. Dx. So I'm just copying this right from up here. And I get the integral from 0 to 6 of m of t dt equals 81.823. And I'm going to do units in a second. And then if I do 1/6 of that same thing, I don't have to recalculate anything. I just have to take this and multiply times 1/6. 13.637. Okay, so in this first one, let's think about what the units would be, because it says using correct units of measure, explain what each of these are. So this one, if I'm just integrating m of t, and m of t was given in cubic yards per hour, what would be the units be here? Whenever you're integrating, taking the antiderivative, this would just be cubic yards. But then this one, this part would be cubic yards, just like that first one is. When I integrate, I get cubic yards. But then divided by 6. 6 what? 6 hours. So let's think about what this means. So this is from 0 to 6. 0 to 6 what? From 0 to 6 hours. Remember, this was the melting rate, So I have to think about, if I integrate, that's how much snow has melted. So from 0 to 6 hours, 81.823 cubic yards of snow has melted. Or I could say it's the change in the melted snow from 0 to 6 hours, but that seems a little weird to say it that way. So I'm just saying from 0 to 6 hours, this much snow has melted. The same thing down here though, from 0 to 6 hours. And then you remember that last page where we said that anytime this was just the average value of this function. So if I'm thinking from 0 to 6 hours, the average, what was this? This is the rate at which snow melts. The average rate at which snow melts. So I'm using the language that they had before. Is 13.637 cubic yards per hour. It's weird, I said cubic yards per hours there, but let's just do hour. Okay, so the first thing wasn't new, but it's bringing it back in your head. We haven't done a ton of this yet, so it's really getting into it this unit. The next one is the new stuff. Like this one you did before, really, but this is the new stuff here. They were thinking, okay, this is the average value of this function, whatever it is. Okay, is the volume of the snow increasing or decreasing? So if a function is increasing, we know that its derivative is positive. If a function is decreasing, its derivative is negative. And so here, if I want to know at time t equals 4, I need to figure out, is the derivative increasing or decreasing? Or in this problem, I could say, is s of 4 greater? Or is m of 4 greater? Or you could say, well, the derivative of this entire function would be s of 4 at 4, I should say, is s of 4 minus m of 4, because this is the rate the snow is being added. This is it's melting. If my value of this, s of 4 minus m of 4, is negative, I know the volume of snow is decreasing. Positive, increasing. So what I can do is I can say, I just want the function value at 4. So here I'm going to do 24 minus, this was t, so, and I can put in 4. I'm up here, by the way. I should move this. I'm putting in 4 into that function. So 24 minus 4, and then put the parentheses. So I've got sine of 4 divided by 14, and then square it. And I'm going to find this value first. I get 23.68225843 minus, now I need to know what it's melting at, so I'm going to go to this other function. 10 plus 8 cosine of 4 over 3. And I get 11,881. So I can say it like this, and then I could say this number is positive, or I could say here, this is justify your answer. So volume, I know that this is going to be positive, so I can say that. Volume is increasing. And you could actually say as the rate the snow is changing on the mountain is positive and then give this answer. Or you could say volume is increasing as S of 4 is greater than M of 4. And this is the rate snow is added. Rate snow is melting. That would be fine. If you want to say this is positive, that's okay too, but then your justification would be a little bit different. You would say volume is increasing as S of 4 minus M of 4 is the rate of change of snow in the mountain at T equals 4, and that's positive. So lots of different ways to do this. How much snow is on the slope after 5 hours? Okay, so this is asking about snow again. How much snow is on the slope? If we're talking about snow on the slope, we've got to go back and we're thinking, okay, I have rates, but I need to integrate it. After 5 hours, so I'm going to go 0 to 5. This is how much snow is being added. This is how much snow is being taken away. Because this is the change in the amount of snow being added from 0 to 5. This is the change that's melting from 0 to 5. We can find both of those with our calculator. But then we have to do one more thing. If it says how much snow is on the slope, we need to figure out how much was there originally. At T equals 0, there were 50 cubic yards of snow. This is an accumulation of change. So this is how much of snow is added, how much it was taken away. If I want to figure out how much is there total, I need to do this. If you would go up, I think that we actually had one of these values, right? I think we did 0 to 6 of S of T. Oh, and we actually did M of T too. Hold on. This one was 0 to 6 of S of T, so I'm just highlighting this. If I push enter, all I'm going to do is change this and say 0 to 5. And I get 50 plus 119.2251162 minus, and I think I already did M of T. Remember that was the one with 10. There we go. I'm going to do this. But this time I'm only going to go from 0 to 5. And I get 73.889799099. Add these up. Well, add and subtract. 50 plus 119.2251162 minus 73.889799099. We get 95.335. And then think about what units this would be. How much snow is on the slope? This was cubic feet. I'm integrating cubic feet per hour. I'm integrating cubic feet per hour. This would be just cubic feet. So at 5 hours, there is this much cubic feet of snow on the slope. Okay, one more. Suppose the snow machine is turned off at time t equals 10. Okay, turned off. Write but do not solve an equation that can be solved to find t equals k when the snow would all be melted. So let's think about this. If the snow is all melted, how much snow is there? How many cubic feet? 0. How much snow do we start with? How do we figure out how much is added? Okay, integrate 0 to, and then I'm integrating, I'm putting 0 right now. I'm not putting anything up here yet, but I'm doing S of t because this is how much snow is added. But do you see how it's turned off at time t equals 10? So I can't add more snow after time t equals 10 hours. but I can keep melting. So I'm going to integrate m of t to figure out how much is melting. I still start at time 0 because snow starts melting right away. But now I'm going to time t equals k. So this looks a little bit crazier than something we've done before, but this is all you need in this problem. You need to know, this is really you understanding that you can integrate how much snow, the rate the snow is being added to figure out how much snow is on the slope or being added to the slope. In this one, you're integrating m of t and you realize that's when snow is melting, that this is an active part of the equation, that you understand the limits of integration. All of this, fantastic free response, like as one whole free response question. This is a frequent problem. It might not be snow, it might be sand sometimes, it might be penguins being added and dying, like so being born and dying. There might be grass clippings. There's all sorts of problems. There's the banana problem one year. These are really common problems. Okay, and I know it's crazy, but we're going to do one more because this is another average value problem. If you want to find the average value on on f of x on this closed interval, and this is from 2003, that's when I graduated. Okay, if I want to find this average value, remember how we said 1 over b minus a of f of x dx from a to b. That will give me average value of the function. Well, if you're going to do it this way, if I say this, so in this case I'm going 0 to 5. And I'm just figuring out this function first of f of x dx. Do you remember how I can split this up? And I can say this is the same integral from 0 to 3 f of x dx plus an integral from 3 to 5 f of x dx. So this is just a rule of integration. I can split integrals up like this. So if I'm doing this one, if I say 0 to 5 and I want to split it up like this, I can, before I do this 1 over b minus a stuff, I can actually just figure out what the integral from 0 to 5 is. So from 0 to 3, I would have the integral of x plus 1 dx plus 3 to 5 minus x dx. And I could actually find both of these values. How, you ask? I could do the area under the curve, but I don't have a curve, so I'm going to do fundamental theorem of calculus. Remember, x plus 1, the square root, is the same thing as this to the 1/2 power, so I'm going to add 1 to the exponent. 1/2 plus 1 would be 3/2 divided by my new exponent. I'm going to integrate this. I can bring the coefficient out in front, so I'm just going to integrate from 0 to 3, multiply by 2/3 at the end. Same thing over here. The antiderivative would be 5x minus 1/2 x squared. F of b minus f of a, so I had up 2/3. If I put in 3 plus 1 is 4 to the 3/2 power, minus 0 plus 1 is 1 to the 3/2 power. Over here, if I put in 5, I would have 25 minus 25 over 2. Substitute in 3, 15 minus 9/2. Okay, multiply all this out. The square root of 4 is 2, cubed is 8, minus 1. Over here, I'm actually going to do some magic over here. I'm going to take 25 minus 15 and get 10. And then negative 25 over 2 minus a negative 9 over 2 would be the same thing as negative 25 over 2 plus 9 over 2. And the reason why I'm doing that is just because it's going to be easier to add these. Negative 25 plus 9 would be negative 16 over 2. Yeah, I'm getting somewhere. 2/3 times 7. Plus, over here, I've got 10 minus 8. And I got 2. I've got 14/3 plus 2, which is the same thing as 6/3, and I end up with 20. Whew! So much algebra. But remember, oh, I didn't even do the last part. I got 20 thirds here. Remember, the average value of the function would be 1 over b minus a. So in this case, I would have to do 1 over, we're going from 0 to 5, of 5 minus 0, f of x dx. But we already found out what this was. So this would be 1/5 times. You can leave it like that, or you can say 20 over 5 is 4. Got all this way, why not say that this whole thing is 4/3? Thanks for sticking with me. I know this was a long one. I think you're great. Bye.